Oh, wait, that was trying to add one question. Sure. Do we ever add like the constraints to these methods or talk
Yeah,
about that?
no,
Okay.
that's a great question. I think constraints makes it challenging.
Yeah,
So there's two ways that you can approach it. We'll go over this kind of later in class. So one way to do the constraints is to kind of do it kind of in the same way as our where you take our constraints and we add it directly to that function.
Okay.
So that, you know, and so that method there is actually called penalty. And so instead of enforcing the constraints exactly, what you're going to do is you're going to analyze the algorithm for searching outside of it.
Interesting.
So you basically add it in a way where like, if it tries to get a point that's outside the range, then you say, all right, you know, that's bad. Bring it back.
Interesting.
The other way to do it is to actually treat it directly within the algorithm, which is it's a lot more complicated. So you actually need new methods for that. So there's all different kinds of things. I'm not sure how much of that we'll get to in the class, but there's, you know, just one of the more popular methods is called projection. So if the algorithm ever gets a point that's outside of the domain, and you basically use projection to project it back into the, or you basically say, what's the closest point within the domain that's closest to that?
Okay.
Yeah.
Couldn't for some of them though, like the elimination methods, you just set it at the start for like, if you know, like, oh, it needs to be at least 3, start with 3,
Yeah,
then.
yeah.
Okay.
Yeah, and typically you do that too. So, you know, for most of these methods, you're going to start with some kind of initial guess. You know, you should.
And your initial guess could kind of imply like a constraint.
Exactly. Yeah. So you usually want to start it within the domain.
That
If you start it outside of the domain, then yeah. So you want to give your algorithm the best chances.
Okay. Cool. Good to know.
Yeah.
All right.
Yeah.
I had a question in terms of the write-up.
Okay.
We have 2 things to take care of: keywords, which we have to reference throughout and everything, and then type them at the very end.
Yeah, don't worry about it. So the keywords are that's normally a component of like a traditional scientific article. Basically, those are your Google search. But for this one, you know, if you want to put them, they'll be like an element, campus, things like that. But you can just take it out. I always forget to take that out of the template. But yeah, don't worry about it.
And as far as formatting, do you want us if like each section is on page?
It doesn't have to be its own page, but as long as they're separated by the headers, then that's.
So if I were to like throw in the title page, give the abstract its own page, maybe throw in a picture at the bottom of the abstract.
Yeah.
And then keep going from there on, giving their own pages,
Yep.
adding pictures to.
Yeah, no, that would be that would be a good way to do it.
Thank you.
So I just have like a question on the analysis, I guess. So I'm gonna do the project and it's like a pretty common part. So I was like, what if someone like sees the rating side, the rating for this sort of loading scenario and not the other one?
Yeah.
So my thing is like, okay, so I'm gonna find the load at which it reaches the yield stress. And then after that, I'm going to convert it. Like the simulation.
Yeah, you only have to do the conversion step on just one configuration, so that's
Okay. I just wanted to make sure that it was enough.
Oh, yeah. Usually you don't do conversion unless it's a very specific case. Usually you just do conversion step on just one configuration. And then you just say that this mesh is good.
Okay.
Yeah, so just putting on one.
So this configurations 1 and 2 can be that and then a loading scenario.
Oh, so, okay. I'm sorry, so the conversion step is mostly just when you do the.
Well, then just the one thing.
So that's usually done kind of in the methodology. So when you're discussing your mesh, usually when you say, people are gonna say like, oh, I have this going on before, and here's my mesh conversion step. So usually
So more.
I'm doing that at the moment. So like, and now still have. There's a bending moment. We think it's gonna create an equivalent force. You just have to calculate what that force is. I mean, it's a
okay.
my team is that. There's pretty much, you know, migrate to them.
Yeah.
And that's the side, it doesn't look towards to this side,
Okay,
and it will be like, I guess, pivot.
okay.
It will be broken about that.
Mhm.
And then there will be a method still connected to this part.
Okay.
But the only thing is that I'm not sure how to, do all of that, because I don't have a constraint for like, I don't have a fixed and.
Yeah, so you're gonna have to approximate. So this comes up often whenever you're doing FEs and this sort of component.
Yeah.
Because normally, you know, or at least what we understand is that we're talking about anchors, right? But if you're doing just a component like this, like the whole part comes into the kind of motion. You know, for me, if for me, and it depends what the test for too. So you said you're, you know, the person's supposed to be honest, kind of pushing it. So I would fix it probably at the pivot, just as an approximation.
Yeah.
Generally, what you're gonna see is that when you apply a fixed constraint to something, it's gonna make it over rigid. And so the stresses that you're gonna get are higher than the practice. In practice, it's as a big one. Right? So that's one way that you can find it out, where you can say that this situation is probably more stressful than the other one.
Mhm.
And if you can design it to fit well here, with the factor of safety, then it's definitely going to be. So the real way to do this, if you wanted to, you know, apply fixed constraint properly to simulate the entire vehicle,
Mhm.
which obviously is not feasible.
Yeah.
So when you're doing kind of subcomponent analysis, you have to kind of make some assumptions.
Okay.
Yep. Very good. You can have prep some. Okay.
For the mesh component.
Mhm.
So I was wondering about the mesh component.
Okay.
But that's the problem that I have two scenarios with three materials, and that's why I have a lot of machine learning.
Usually for mesh conversion sets, you just go for one material, load.
Okay, yeah.
And then if it converges well for that, then you say, okay, that should work. It's pretty rare, unless you have voting scenarios that are very, very different from each other, you have your like weight that's even in professional.
No, okay.
Yeah, usually you have some. But if you ran all the tests, you might want to do all the tests.
Yeah.
Don't throw it out.
Takes
So
a lot
yeah,
of time. to make this,
yeah, so I mean, if you have it all, you know, include it, but yeah, typically you only.
Yeah, it's not like it's not okay, not, yeah. I wanted to know for the final, like, the final
Yeah.
project, and there's, yeah, thank you.
Yep.
Right. But yeah, I think about it. Let's see this direction. Right, and you're pushing off this way, it's gonna be resisting the bottom part of it, so it's the other direction. Take the side section, putting this like a non-zero, take the side section. Um, Whoa. Yeah. I gotta ask you a question. All right.
Wow, we just shine all the pictures. Oh, okay.
I got a variety.
Oh, all these are nice. I like this one. I like the combination. Thank you.
This one's not shiny.
Yeah. You gotta go for some shines.
And this one is not Russian.
Wow, yeah, that's the traditional one. This was made for this one. This is nice.
You missed the first international.
International, as in they had.
Qatar,
Really?
they got initiated last convention last year.
Wow.
This year, Connecticut, I was in Connecticut, that's what I was doing I was doing petitions.
Oh, okay.
So we were trying to be like, do we let them in, do we not let them in? It was that was a quick vote. They also wanted us to change the bylaws.
I see, I see.
That's what we all argued about that.
Yeah.
And then we went a whole circle and we're just like, you know what? What we didn't change was better. So we just went back to the start and then we admitted it. No one objected and we're just like,
That's fun though, that's exciting.
we could have slept.
That's professional meetings and
You want more stickers?
I'll just take this one.
You sure?
Yeah,
Okay.
thank you.
Laughing. And my stylist died, so notes is gonna be hard to get.
Oh. Okay, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? On the eve of the midterm project being due. Well, 2 days before it's due, I guess. All right, good. All right, so today we just have kind of another standard lecture. So I know everyone's busy with the midterm project. So today we're going to be doing example problems with 2D trusses. So last Thursday when we met, we introduced the idea of how we need to modify our element stiffness matrix when we have 2D problems. So I think we started an example last time. We didn't really get too far, so we're going to start with that today. And I basically just have a couple of examples for you today. So that's about it. So just some reminders. Remember your midterm project is due this Thursday. So that is Halloween, October 31st by 11:59 p.m. Already seen a couple people turn it in, so thank you guys for turning it in. I will work on grading it on Friday and next week, so I should hopefully have your grades by Thursday of next week. Okay. So I've gotten a lot of questions on the midterm project. Just remember that the simulations themselves for the midterm project are not meant to be overly complicated. So kind of what I'm seeing is that people are kind of tending to be more on the side of kind of overthinking their loading, overthinking their scenarios. So you don't have to overthink those. It was meant to kind of be that part was meant to be relatively straightforward. What I'm really grading you on, remember, is the quality of your write-up, the quality of your report. Okay. So some common questions that I've gotten over the last couple of days is, in the report, you're going to be required to write a lot of data tables. And so data tables for the material properties, for some of the meshing parameters that you may have, maybe your results have some data tables. So, especially for the material properties, one thing I saw a lot last year was people just took a screenshot of kind of the material property thing and ANSYS. Typically, for a professional report like this, you want to avoid taking as many screenshots as possible. If you have the ability to kind of create a table yourself and input the data manually, that's always going to look a lot cleaner than just taking a screenshot of a data table. So I would definitely prefer that. kind of the situation where you can't really avoid a screenshot is when you're showing your ANSYS results. So things like your deformation field, your equivalent stress field. People have asked me some questions on that. So typically what I recommend for those figures is to make sure that you show the model as much as possible. I don't need to see all of the kind of the ANSYS stuff like the ANSYS interface. I just want to see the colors on your model, and I want to see the color legend so I can know kind of what I'm really looking at, and try to center it as much as possible. Okay, question, yes.
Does the situation have to be made this?
To a certain degree, but you can go into the realm of fantasy a little bit. So you can say like Superman is pulling on this thing or something like that. But I don't want a situation where you have your handle and then it's going to be spontaneously generating this huge magnetic force on itself. So it should be reasonable in terms of what you can expect the use case for that object is, but the magnitudes of the forces and the exact scenario you can be a little bit creative, if that makes sense. Okay, any other questions on the midterm project? Okay, another announcement I wanted to make. So, for the past few weeks, we've been talking about, the direct stiffness method. So I haven't given you any assignments on that, just because I wanted to just make sure that you guys could focus on the midterm project. But since the midterm project is due this Thursday, I'm planning on posting a problem set tomorrow, probably tomorrow night. So you can start working on that. Okay. And for the problem set, the plan is for you to, my plan is to give you a couple weeks to work on that. And that should take us up to the midterm exam, which is going to be right before Thanksgiving. Okay. So the next few weeks are going to be pretty busy. This is probably the busiest few weeks in this class, just because, a lot of people are finishing up the midterm project, but we also need to start preparing for the midterm exam right before Thanksgiving. So November is pretty busy for this class, just kind of be. Okay. All right, any questions I can answer before we get started for today? Okay, all right, so let's go ahead and pick up where we left off. And so what we were talking about last Thursday was direct stiffness methods with 2D geometries. Okay. So, before we get back into the example that we're doing last Thursday, I do want to kind of summarize a few of the key points here. Okay. So the main key point when we're working in 2D is that it changes our element stiffness matrix. Okay. And there's a few reasons for this, right? So the main reason it changes is because we have to account, now that we are looking at 2 dimensions, we have to account for the specific orientation of the element itself. Okay. Because no longer are we going to have situations where all of our elements are perfectly parallel to each other within the same line. So we may have elements that are facing different directions, and we need to account for that in our element stiffness matrix. Okay. Another big reason why our element stiffness matrices change is we have to account for deformations in 2 dimensions now. Okay. Before, all of our deformations were just in the X direction, so now we can go in the Y direction as well. Okay. And so, the upside to this is that now our element stiffness matrix is going to be 4 by 4 instead of 2 by 2. Okay. And and it contains a lot of sines and cosines. All right, I guess instead of writing that, let me just kind of give you the exact element stiffness matrix. Okay, so the element stiffness matrix for a 2D truss is, okay, looks like the following. So our four components here are going to be D1x, D1y, D2x, D2y. Okay, and I'm going to label those same columns as well. Okay, so D1x, D1y, that is the x and y deformations of the first node in our element. D2x and D2y are the x and y deformations of the second node in the element. Okay. Okay. And remember kind of the shorthand notation that we used last time was I'm using the letter C to represent cosine of the angle theta. Okay. Where theta is the angular representation of the orientation of that element. And then S is sine of theta. Okay. All right, so our element stiffness matrix is the following. So we have cosine squared, cosine sine, minus cosine squared, minus cosine sine. Okay. So that is the first row in our matrix. Second row, so remember, for all subsequent rows, we're starting with the diagonal term and just going to the right, because remember, our element stiffness matrix is symmetric. Okay. So second row, we have S squared, minus cosine sine, minus sine squared. Okay. Third row, we start with a third column. We have cosine squared, cosine sine. And then for the fourth row, we just have the bottom right entry, which is just sine squared. Okay. And for everything else, remember that our matrix here is symmetric. All right. So there's quite a bit more to compute. It's computing the element stiffness matrices for 2D problems is quite a bit more of an ordeal. Oh, I forgot the most important thing. We can't forget the truss parameters out in front. So remember, out in front of this matrix, we have A, which is the cross-sectional area, multiplied by the Young's modulus E, divided by the length of the element itself. All right. But that's the biggest change. And so when we're doing problems in 2D, the only thing that really changes is the element stiffness matrix, but the process of assembly, the process of applying the boundary conditions, those are mostly all the same, with just a couple modifications with, just by the multi stuff. But by far the biggest change is the element stiffness matrix. Okay, any questions on that before we jump back into our example? Okay, all right, so let's jump back into the example that we started last Thursday. Okay, so for this example, we have a 3-element system. Okay, so first we have a vertical element. It's kind of hanging from the ceiling just like that. Okay, that's element A. Okay. We have a horizontal element that's connected right at the bottom. We'll call this element B. And then we have a diagonal element that is actually a spring in this case. Or excuse me, the spring is element B, the horizontal element is element C. Sorry, my brain's not 100% there. Okay. So that is our 3 elements there. The angles between all of these is 45 degrees. And then for the nodes, we have node 1 that is on the bottom left. Node 2 is fixed to the wall, connected to element A. Node 3 is connected to the wall, connected to element B. And node 4 is connected to the wall, connected to element C. All right. We have a force pulling on this entire assembly of 10,000 pounds. And then the properties for the two trusses. Okay. Our trusses are elements A and C. Our properties for this are the Young's modulus is 30 times 10 to the 6 psi. The cross-sectional area is 2" squared, and the length is 10 feet. Okay, and then for the spring only has one property, which is its spring constant, K. Okay, so the spring constant for the spring is 250,000 pound per inch. Okay, so that's the problem. I think, we kind of started this problem last week. And so what we want to compute let's compute the deformation of node 1. And we're going to use the direct stiffness method. Okay. So that's just kind of a rehash of last time. But, just wanted to make sure that we have it all in minutes. Okay, so let's go ahead and start our method here. So just like any direct stiffness problem, we're starting with our element stiffness matrices. Okay. And remember, before you write the element stiffness matrix for each element, you want to be aware of kind of some key properties of each element. Okay. And so let me go ahead and number the ones that you should be aware of. Okay. Because this list grows a little bit in 2D. So when you're writing your element stiffness matrices, first thing you should be aware of are the element properties. Okay. So that is like your A, your E, your L. Okay. All right. So that doesn't change. Right. And so that's kind of the same as 1D. You need to compute its effective spring constant based on its physical properties. Okay. We need to be aware of the nodes that it's connected to. So remember, this is the most important thing that we need to do, that we need when we perform assembly. Okay. And the third thing to be aware of is the element's orientation. So this third one's new. So we didn't have to take this into account in 1D, but all of our elements were in the same orientation. Okay. Specifically, when I say orientation, what I mean is orientation relative to the positive x-axis. So that's not going to be as important for this example, but it will be actually very important for the next one that we're going to do. Okay. All right. So with those three things in mind, let's write out the element stiffness matrices for each element. Okay. Okay. So let's start with element A. So element A, let's compute our physical property. So we have AE over L. Okay. So that's just the coefficient that goes in front of our element stiffness matrix. So we're just going to plug in our area, our Young's modulus, and our length, making sure that everything is in the same units. Okay. And so we plug all of it in, we get an AE over L of 5 times 10 to the 5th pounds per inch. Okay. The node that it's connected to, element A is connected to nodes 1 and 2. Right, so we'll make note of that when we're writing out the node indices. And last thing that we're going to be writing down here is the orientation, which is the angle. Okay, so the angle of element A is 90 degrees. Okay, so if you look back at element A, you can see that relative to the positive x-axis here, the orientation is 45 plus 45, which is 90. Okay. And so based on the angle here, we can compute cosine and sine of that angle. Okay. Just because we're going to be plugging it into our element stiffness matrix on lot A. Okay. All right, so cosine of 90, very simple. Cosine of 90 degrees is 0, and sine of 90 degrees is just 1. Okay. So let's go ahead and plug all of these into our element stiffness matrix. Okay, so our element stiffness matrix is going to start with our factor AE over L in front. So that's 5 times 10 to the 5th. Okay. And then we're going to start plugging in values of sine and cosine. Okay. So first row has all cosines attached to it. So this is all going to be zeros. Okay. Second row. And we did this one last time, so I'm just going a little bit quicker today. And so you plug in all the values for sine and cosine that were involved in this element stiffness matrix. We're just plugging everything into this expression up here. And then we end up with the following matrix. Okay. And then, of course, we need to label the nodes that this is attached to. We have D1x, D1y, D2x, D2y. So when you have elements that are oriented either 0 degrees or 90 degrees, your life is pretty nice because you end up with a lot of zeros in the element stiffness. All right, any questions on how we got this matrix here? Okay, good. All right, so let's move on to element B. Okay, so for element B is a spring. And so springs, they only have one property that's associated with them, which is the spring constant. And so that's 250 K. But we can write this in scientific notation just to be consistent with above. Right? So 250,000 is the same thing as 2.5 times 10 to the 5th. The units for that is pounds per inches. Okay, so let's look at the nodes. And so let's go back up to the spring up here. Okay. It's going to be a little bit interesting when we do the assembly, but we can see that element B here is connected to nodes 1 and 3. All right, so we want to make sure we make note of that when we're writing our element stiffness. All right, and then our orientation, our theta here. So if we draw the positive x-axis and we see how this element is oriented relative to that, we can see that the orientation is 45 degrees. Okay, so let's go ahead and account for that in our calculations down here. So theta here is 45 degrees. And so let's go ahead and compute sine and cosine of 45 degrees. So both sine and cosine of 45 degrees is root 2 over 2. All right, so now we're going to start plugging these into our element stiffness matrix. Okay. Okay, so let me go ahead and draw our 4x4 matrix. Okay, let me go ahead and write the nodes that it's attached to as well. So we have d1x, d1y, and then d3x, d3y. Okay. All right, so this one's going to take a bit more work compared to our zeros and ones here, but you know, thankfully it's just all products of root 2 over 2, just with different signs. Okay. Okay, so let's go back up to our formula for our element stiffness matrix, and we'll just go row by row. Okay. So first row we have cosine squared and then cosine sine. So let me go ahead and write those two entries in the first two. Okay. So cosine squared, that's going to be root 2 over 2 squared. And then cosine sine, we have root 2 over 2 multiplied by root 2 over 2. Okay. All right, so the next two entries in the first row, we have a minus cosine squared and a minus cosine sine. Okay. We have minus root 2 over 2 squared, and then root 2 over 2, and root 2 over 2. And I'm regretting not giving myself some more space there. Okay, so they're all products of root 2 over 2, just, you know, some of them have a plus sign, some of them have a minus sign. So I'm just going to go ahead and simplify this. I'm sorry, there should be a minus sign on the last entry of that first row. Okay. So we know that root 2 over 2 multiplied by root 2 over 2 is just 2 over 4, which is the same thing as 1/2. Okay, so I'm going to replace everything here with 1/2. Okay, so in the top left here, we have 1/2. Next to that, we have 1/2, then a minus 1/2, and then a minus 1/2. Okay. Okay. Before we move on to the next row, let's go ahead and do our trick. So let's take advantage of the fact that our element stiffness matrix is symmetric, and then just take this first row, and we're going to write that first row down into our first column. Okay, so we have a 1/2 in the second row, first column, minus 1/2 in the third row, first column, and then a minus 1/2 in the fourth row in the first column. Okay. Okay. Remember, don't forget our symmetric trick here. So it can save you a lot of time, especially once we get to beams, which is the next unit, which we'll probably start on Thursday. Okay, so let me go ahead and erase these. Okay, so now let's go to the second row. So second row, we have sine squared. So sine squared, that's root 2 over 2 times root 2 over 2, which is a positive 1/2. Okay. And then from there, we have a minus, I believe, cosine sine. Yep. So minus cosine sine, that's a minus 1 over 2. And then at the end of the row, we have a minus sine squared. So that's a minus 1/2. Okay. Okay. Once again, we're going to write these two entries into the corresponding column. So we're going to have a minus 1/2 and a minus 1/2. Okay, good. All right, so for the last two rows here, it's pretty straightforward. So we have a cosine squared, so that's 1/2, and then a positive cosine sine, so that is 1/2 as well. Okay. And so once again, we're going to write this down into the appropriate column. Okay. The 1/2 at the end right there will become a 1/2, kind of on the bottom, last row, third column. Okay, and then the for the final entry there, we just have sine squared, and so sine squared is just √2/2 times √2/2, which is 1/2. All right. So I did this fairly quickly, just because this is probably, I don't know, maybe the 70th or 80th time that I've computed this matrix here. But when you're first starting out, it's take your time. So it's it's a 4x4 matrix. So that means there are 16 calculations that you have to do. It's very, very easy to make mistakes doing these things. Just because the temptation is to kind of try to go fast. Just because just because you're kind of getting tired of it. I understand. But when you're going fast, it's very easy to kind of miss a negative or miss a number in your calculator. So kind of really take your time when you're doing these problem sets. It's very easy to make a small mistake, and that small mistake ends up kind of propagating quite heavily. So you want to make sure you kind of take your time. Okay. All right, any questions on this? Okay. All right, we have one more element. So this one I'm going to go fairly quickly. Okay, so element C here. First, we need its A/L factor. So element C is another truss element. We need to take its cross-sectional area multiplied by its Young's modulus divided by the length. So this is identical to element A. So we end up with 5 times 10 to the 5th pound per inch. Okay. The nodes that element A is connected to, or element C is connected to, is 1 and 4. Okay. And then the orientation theta. It turns out that element C is actually parallel to the x-axis, so its orientation theta is just 0 degrees. Okay. Okay, so that saves us a lot of work actually. So cosine of 0 is 1, and sine of 0 degrees is just 0. Okay. So that tells us that anything that involves sine in our element stiffness matrix is just going to go away. Okay, so very quickly, let's go ahead and write out the element stiffness matrix. Give myself a little bit more room this time. Okay. Okay, so our factor out in front is going to be 5 times 10 to the 5th. And then the vector that's multiplying it is d1x, d1y. Those are the 2 degrees of freedom for node 1. And then we have d4x and d4y. That's the 2 degrees of freedom for node 4. Okay. So I'm just going to fill this in very quickly here, but just basically the only times you have a non-zero entry for a 0 degree orientation element is when you have cosine times cosine. So anything that has sine multiplied by it is going to be 0. Okay, so our first row is going to be 1, 0, minus 1, 0. Okay. I'm going to write that into the first column. We have 0, minus 1, 0. Okay. Second row is just going to be all zeros because everything in the second row involves sine. Same thing for that column as well. Third row, we have a 1 and a 0. So I'm going to write that 0 down into the bottom right. And then finally, the last term there at the bottom, very bottom right, fourth row, fourth column is going to be sine squared. All right, so this is our element stiffness matrix for element C. Okay, good. All right, so that's our 3 element stiffness matrices. So we're now ready to move on to the next step. So the next step in our direct stiffness method is to assemble. Okay, so remember for assembly, we want to combine this together all into one, global matrix. All right, so first thing we need to determine is the size of our global matrix. Okay? Now you have to be careful here because before in the past with 1D problems, the size of our matrix just corresponded to how many nodes that we have in our system. Okay. But now that we're in 2D, each of our nodes here actually have 2 degrees of freedom. So each node has both an X displacement and a Y displacement. Okay. So that means the size of our matrix in this case is going to be number of nodes multiplied by 2. Okay. So we have 4 nodes in the system. And if for each of those nodes have 2 degrees of freedom, that means our stiffness, our global stiffness system will be 8 by 8. Okay. So this is going to be pretty big. So I'm going to try to use as much space as I can. Okay, so let me write the columns first just to make sure I have enough room for everything. Okay. So each node, nodes 1 through 4, is going to have both an X displacement and a Y displacement. So I'm going to start with node 1. We have D1X, D1Y, D2X, D2Y, D3X, D3Y, D4X, D4Y. Okay, and then we'll write in the rows. So we have D1X, D1Y, D2X, D2Y, D3X, D3Y, D4X, D4Y. Okay. We have a massive system here, right? So assembly is going to be a little bit more, not more complicated, but just, you have to give yourself more space on your paper to write them. Okay. So just like we've done before, I'm going to write out our three elements here. Okay. And then before I actually start filling in the each of the matrices, I'm just going to block off all the areas where we're going to insert this. Okay. All right, so let's start with element A. So element A is pretty straightforward. So element A is just nodes 1 and 2. So all the rows and all the columns that have to do with nodes 1 and 2, we're going to circle them with element A. Okay. Okay, so that means that's just the first 4 rows and the first 4 columns. Okay. So that's going to be approximately that area right there. Okay, element B. If we look back to our element stiffness matrices, we know that element B consists of nodes 1 and 3. Okay. Okay, so this is where things get a bit complicated. So we're going to have to split this up, right? So we've done this before. So in our 1D problems, we've had situations where we had to split up our element stiffness matrix. This one it's a bit more complicated because we have a 4 by 4. Okay. So basically, all the rows and all the columns that have to do with nodes 1 and 3, we're going to circle them for element B. Okay. Okay, so first one, let's do node 1, node 1. So that's going to be the first 2 rows and the first 2 columns. Okay. So that one's pretty easy, and so we need to make sure we circle that one there. Okay. Now the next ones are going to be in batches of 2 by 2s. Okay. Next, we're going to have node 1 and node 3. So that's going to be the first 2 rows and then the 5th and 6th columns. So that's that region right there, right? And so remember, it's a 2 by 2 region. And then same thing on the other side. So we have the first two columns and then the fifth and sixth rows. So the intersection between those areas is this section right here. All right, and then finally we have the fifth and sixth row and the fifth and sixth columns, because those are the rows and columns associated with node 3. Okay? So that is this area right here. Okay, good. All right, and then finally we have the entries for element C. Okay, so element C is nodes 1 and 4. Okay, so we're going to do the same thing here. So we're going to take our element stiffness matrix, we're going to split it in 4, just because those two nodes are not next to each other in the matrix. Okay? So it's going to look similar to our sections here for element B, except everything's going to be pushed out one more just because they're for node 4. Okay. Okay. So first thing is we have the entries for node 1. So that actually overlaps up here. So it's a big party up in the top left of the matrix. Okay. Then we have this area here on the right. So it's the first two rows associated with node 1, and then the last two columns associated with node 4. Okay. And then we have the same thing on the bottom left. So the first two columns associated with node 1, the last two rows associated with node 4. And then we have the last two rows and the last two columns associated both with node 4. Okay. So that is the all the areas, right? So before we start filling in all the entries of the element stiffness matrices, let's fill in all the blanks. So remember, everything that's not covered by an element stiffness matrix, we're just going to fill it in with zeros. Okay. So we have a 0 here, 0 here, 0 here, 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 here. All these areas right here. All right. So now we can start filling in the entries here. Okay. And remember, whenever you have element stiffness matrices that overlap, you're going to add those entries together. Okay. Okay. So you want to be careful here, just because of not only are you adding in together the entries in the matrix, but you also have to remember that each of these matrices have a constant factor that's being multiplied out in front as well. Okay. Okay, so let me do this. And so, just so that we don't have to write out 10 to the 5th every single time, I'm going to say that in front here, we're going to have a 10 to the 5th out here. Okay. All right, so we're going to have a factor of 10 to the 5th multiplied by the front of the matrix. Okay, so we don't have to keep writing 10 to the 5th on the inside. Okay. Okay. So let's start with the element A. Okay. So element A. I'm only going to write out the non-zero entries just because, the zeros are going to get redundant. Okay. So element A, we have a 5 times 10 to the 5th right here. Okay. We have a -5 right here. You have a -5 right here, and then a +5 right down there. Okay. Okay. All right, so now let's go to element B. So element B is going to be a little bit more complicated here. Okay. So element B, we have a bunch of 1/2s, and we have 1/2 times 2.5 times 10 to the 5th. Okay. So if we factor out 10 to the 5th out in front, that means inside the matrix, we're just going to have 1/2 times 2.5. Okay. Which is not a convenient number, and I don't know why I did this. Okay. So for all the entries that are circled in blue there, we're going to fill in all those entries. Okay. So in the top left 2x2 part of the element B matrix is 1.25, positive 1.25, positive 1.25, positive 1.25. Okay. And in the bottom right part of this matrix here, we have two entries overlapping. And so remember, whenever we have entries overlapping, we're going to add their values together. So let me just kind of clean it up a little bit. Okay. So in the bottom left, and the bottom right entry of the top left portion, we have 1.25 plus 5. Okay, so let me go ahead and fill in the rest here. So we have minus 1.25, minus 1.25, minus 1.25, minus 1.25. Okay. And we have minus 1.25, minus 1.25, minus 1.25, minus 1.25. Okay. And then on the right here, we have positive 1.25. All right, slowly but surely, the matrix is coming together. All right, and then finally we have the green, which is element C. Okay, so once again, I'm only going to write out the non-zero entries. But if you look at the green matrix here, okay, we have 1, -1, -1, and 1, all in the top left corners of each of the 2x2 sections here. Okay. So if you look at how this matrix is assembled in the global stiffness system, you can see that I've taken each of these kind of 2x2 sections and kind of split them up into different portions. Okay. Okay, so let's go ahead and fill those in. And so in the top left right here, we have a +5. Okay. Up here, we have a -5. Over here, we have a -5. And in the bottom right, we have a +5. Okay. Okay. And then at this point, we can fill in everything that's not filled. So everything that doesn't have a number there, we can just go ahead and fill in zeros. Okay. So that's the assembly. So, assembly, a bit more complicated here just because there's multiple degrees of freedom per node. So again, make sure you guys are doing this slowly and carefully. Because there's, I can't tell you the amount of times that, these matrices get mixed up because you're off by a row. Okay. All right. Any questions on this part here? Okay. Good. All right. So the last thing we need to do before we can solve this is to apply the boundary conditions, right? Because remember, at this point after assembly, this set of equations, we can't solve it because this matrix is actually still perfectly symmetric. And so we need to apply boundary conditions to solve this guy. Okay. So So we have quite a few boundary conditions in this case. We have 3 constraints and 1 load. Okay. So we have constraints on nodes 2, 3, and 4. So actually the only node that's free here is node 1. Okay. So we're going to apply constraint boundary conditions on all of those rows. And since these are pin supports, they're actually going to constrain both the X and Y deformations. So that means rows 3, 4, 5, 6, 7, and 8 are all going to be wiped out by the boundary. So we spent all this effort to build this beautiful matrix only to wipe most of it out with the boundary conditions. All right. And then we have 1 load, right? And so if you go back to the figure in our problem, we have 1 load of 10,000 pounds. Okay. This is acting on node 1. Okay. And it's acting in the negative Y direction. Okay. So that's important. So, now the direction of the modes is going to be very important when we're applying this to the matrix. Okay, so let's go ahead and apply these boundary conditions to this matrix up here. And in fact, let me go ahead and write the right-hand side vector because we're going to need it for the boundary conditions. Okay. I'm going to say this whole thing is equal to F1x, F1y, F2x, F2y, F3x, F3y, F4x, F4y. Okay, so remember all of those little F's, they represent the forces that are acting on those nodes, specifically in the X and Y directions. Okay, so let's start with the constraints. And so, the constraints for this one are fairly straightforward. They're just, kind of annoying to apply just because there's so many. Okay, so node 2. So let's apply the constraint on node 2. So that means we're going to wipe out this entire row right here. Okay. And we're going to wipe out both rows, right? So remember, node 2 is completely pinned to the wall. So that means both its X and Y deformations are going to be constrained. Okay. We're going to wipe out both of those rows. We're going to put a 1 on the diagonal entry and zeros everywhere else. Okay. Okay. So for the third row, that means we're going to put a 1 in the third column there. Okay. I don't like the orange on orange. Use purple. Okay. So everything else in that third row is already 0, so we don't need to change it. And then on the right-hand side, F2x, we're going to change that to 0. Okay. So that is the constraint being applied on node 2. Okay. Or excuse me, yeah, the X component of node 2. Okay. For the Y component of node 2, we're going to replace this entire row with zeros, except for the diagonal entry. So the diagonal entry for the Y component of node 2, that's in the 4th row. So that means we're going to put a 1 in the 4th column. Okay. And then on the right-hand side, we're going to put a 0. Okay. So I'm going to do the same things for node 3 and 4. So that means for the entire bottom half of this matrix is going to look just like that. Okay. So I'm going to replace the entire row with zeros, except for the diagonal entry. I'm going to put a 1 there. Okay. So I'm going to do this just fairly quickly, just in the interest of time. We have zeros here, a 1 here, 0 and 0. We have 0, 0, 0, 1, 0. And then for the last row, I'm going to replace these with zeros. Okay. So for the 7th row, we have 0, and then a 1 in the 7th column, and a 0 on the right-hand side. And then on the last row, we have all zeros, except for a 1 in the 8th column, and then a 0 on the right-hand side. Okay. Okay. All right, so all of our constraints are applied, right? So all nodes 2, 3, and 4, both the x and y directions on those nodes are constrained. Okay. Now we have to apply our load now. So our load, we know our load has a magnitude of 10,000 pounds, and it's acting on node 1 in the y direction. Okay. So you want to be careful here. So when you're applying your loads, you want to make sure that you apply it on the right component of the force. Okay. So since our load here is being applied on node 2, okay, or excuse me, on node 1 in the y direction, that means we're going to put the load magnitude there. Okay. And so our load magnitude is 10,000 pounds, and we know that it's going in the minus y direction. And so that means in the second row, we're going to have a minus 10,000 on that one. And there's no load being applied in the x direction on node 1. We're just going to put a 0 on that row. Okay. Okay. All right, so finally we arrive at this matrix here. So it's quite gargantuan, but we're ready to solve. So what we can do now is we can plug this into MATLAB. Okay. And we can solve for the results. Okay, so we have 8 results here. So we have x deformation and y deformation for each of the 4 nodes. Okay, so if we plug this into MATLAB and we solve for it, what we get is we have d1x, d1y. These are the only solutions of note here. Everything else is going to be 0. So d1x is going to be 0.0033 inches. Okay. And then d1y is a minus 0.0167 inches. Okay. We have d2x, d2y, both of these are 0. d3x, d3y, both of these are 0. d4x, d4y, both of these are also 0. All right. So that's the problem. So, took us a better part of an hour to do this, but in reality, you're going to be going a little bit faster. First of all, because you don't have to narrate every single one of your steps like I have to do. But these problems they can still be fairly lengthy. All right, any questions on this example here? Okay. All right, so the thing with these direct stiffness problems, they are very tedious. There's kind of no way around that. I'm not going to pretend like they're not. I'm not going to pretend like this is fun for me too, but we have to go through this theory. You have to come away with some of that from this class. Okay. So again, but the nice thing about these problems is that it's fairly systematic, and so every single problem kind of follows the exact same process. And so if you think about it, so there's not really much thinking that you have to do. You just kind of have to just follow the process. You just have to make sure that you're kind of disciplined in terms of, computing things correctly, plugging things in correctly, negatives are in the right place. Just because that's where most of the mistakes end up coming from, right? Okay, so I do have one more example that I want to go through with you, but I don't think we'll have time for it today. But what I want to do instead is talk about something interesting you could actually do with these results. Okay. So if you think about, our ANSYS activities, right? One quantity that we always compute in the ANSYS activities is the stress, right? Well, one thing that I've mentioned a lot in this class is, as I said, that stress is a derived quantity, right? What that means is that it's not the first thing that ANSYS is going to compute. So the first thing ANSYS computes is the deformation, and then from the deformation, from there, it computes the stress. So last thing I wanted to show you today is kind of how that is actually taking place, right? Or how that actually happens. So we've gone through this example here. We've computed the deformations of the nodes. So what we can do now is we can take these deformations and use them to compute stress in each of the elements. Okay. So let's talk about how to compute stress in a truss element. Okay. So let's kind of review our definition for the stress. Okay. So if you think back to kind of the early, I think maybe in the second or third week in the class, we talked about this idea of stress being kind of an internal force within the member itself. Okay. We can come up with a very simplified expression for stress for a truss bar, because what do we know about the forces on a truss? The forces on a truss are always going to be down the axial length of the member. Okay. And so for a truss member that may look something like this, okay, we know that to be in static equilibrium, we have to have an equal and opposite force on both sides. Okay. So that means there's no other forces acting on these members here. So that means the stress here is just going to be the force divided by a cross-sectional area. Okay. So how do we apply this formula to our finite element result? Well, right, one thing we notice is that in this diagram, our forces are being applied at the endpoints of the element. And so, right, if we think back to how we derive our truss element here and how our element stiffness matrices are defined, right? We actually have expressions for the forces at the ends of these nodes, right? So another expression for the forces applied at the ends are the nodal forces in the local reference frame. Okay. And so we can replace this formula here. And so instead of being just some generic force F, right, we can choose one of the nodal forces that are acting on our element. So it doesn't really matter because our element here is in static equilibrium. So we can choose either F1 hat or F2 hat. Okay. So let me go ahead and just select F2 hat. Okay. And in particular, we want the F2 hat that's in the direction of the element itself. So that's F2 x hat divided by K. Okay. So what we can do from here, right, So now that we kind of established that, if we can compute the local nodal force that's acting on the endpoint of the element, then we can compute the stress of the element. Okay. 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 So how are we going to get our expression for F2x hat? Well, we actually can get a clever expression for this from our local element stiffness matrix. Okay? Remember, this is the local one. So this is without all the sines and cosines. This is just our 1D element stiffness matrix. Okay? So our local element stiffness matrix looks like this. We have A over L multiplied by 1 minus 1 minus 1 minus 1 and 1. Okay. This is D1x hat. D2x hat is equal to F1x hat, F2x hat. Okay. So remember, this is local to the element. So we haven't taken into account the y direction or any orientation just yet. We will in a second, but just this is just for now. Okay. All right. So if we take the last row in this matrix, right? The last row in this matrix will give us an expression for F2x hat. Okay. So from that last row, we can say that F2x hat, so just simply performing the matrix vector multiplication, is equal to A over L multiplied by vector minus 1 and 1 multiplied by vector D1x hat, D2x hat. Okay. All right, so of course, these, all of these are local quantities here. So remember, when we solve our finite element problem, we don't solve for things in the local quantities. We solve for things in the reference quantities, right? Reference D1x, D1y without any hats. So what we want to do from here is we want to transform just this section into the reference frame using our transformation matrix. Okay. And so that means we're going to have some sines and cosines here, and that minus 1, 1 is going to be expanded. Okay. So I'll just kind of give you the upshot here. And so performing those calculations here, we have F2x hat is equal to AE over L multiplied by the vector minus cosine minus sine cosine sine. Okay. And then you're going to multiply this by the nodal deformations, but in the reference frame. So this is going to be D1x, no hat, D1y, no hat, D2x, D2y, no hats. Okay. Okay. So then to compute the stress, right, come back up here. The stress is just F2x hat divided by A, right? And so that's actually very straightforward to do because we have an A that's out here. So if we just cancel that out, we get the stress in the element is equal to E over L multiplied by minus cosine minus sine cosine sine, okay? That is a 1/4 vector, a row vector, multiplied by D1x, D1y, D2x, D2y. Okay, so this formula here will give you stress in the element. Okay. So there's a couple things to note here. And so first thing to note here is that you can see that we have the appearance of sines and cosines. And so this formula here depends on the orientation of the element. Okay. So this part right here depends on the orientation of the element. Okay. And then this vector right here, the d1x, d2y, or d1x, d1y, d2x, d2y, these are the nodal deformations of the nodes that are attached to that element. Now, in this formula here, I use 1 and 2 just because I have just a generic element. But when you're applying this formula to an element for a particular problem, you want to make sure that you plug in the deformations for that particular element. Okay. Okay. All right, so let's go ahead and apply this formula to our problem, right? So in our previous example problem, we had two truss elements. We had element A and element C. Okay. So let's apply this formula to compute the stresses in those two elements. Okay. So let's do element A first. Okay. All right, so just to remind ourselves, element A is that one vertical element. So theta here is 90 degrees. Okay. And the node that is connected to are 1 and 2. Okay. Okay, so if we compute the stress in element A, this equal to the Young's modulus divided by its length multiplied by. So we have 90 degrees. So we're going to plug in 90 into this vector of sines and cosines. So cosine of 90 is 0. Sine of 90 is 1. So we have a minus sign. So minus sign is minus 1. Okay. Then we have cosine of 90, which is 0. And then sine of 90, which is just 1. Okay. And we're going to multiply this by the vector of deformations of the nodes that are connected to this element. So we have d1x, d1y, d2x, or d2x, and d2y. Okay. Okay. And actually, let me label this the entries in the sine and cosine vector. So this is minus cosine, minus sine, cosine, and sine. Okay, so let's write in our deformations. And so this is our solution. So again, this is something you can only do after you apply the boundary conditions and solve. Okay. And so based on the solutions to our finite element system, d1x here is 0.0033 inches. Okay. d1y here is a minus 0.0167 inches. Okay. d2x here is 0 inches, and d2y here is 0 inches. Okay. So we go ahead and plug this in. We plug in all the variables there, the Young's modulus and the length. We do the vector multiplication, which in this case just ends up being a dot product between those two vectors. Okay. And we end up with a stress of 4,175 PSI. Notice how this is a positive number, and so the sign of the stress that you get actually has some meaning. Okay. So the fact that this is a positive number tells you that element A is in tension. Okay. A positive stress means that the element is in tension. Okay. Okay, and so let me just do the same thing for element C very quickly before we head out. Okay. So element C, the orientation for that is 0. And element C is connected to nodes 1 and 4. Okay. Okay, so sigma C is equal to E over L multiplied by, we have minus cosine. So cosine of 0 is 1. So we have minus 1. And then sine, minus sine is 0. Cosine is 1. Sine is 0. Okay. Multiplied by d1x, d1y, d4x, d4y. Okay. d1x is a positive 0.0033 inches. d1y here is a minus 0.0167 inches. d4x, d4y are both 0. Okay. So once again, if we do the vector multiplication, we do the dot product, we factor in the E and the L. What we get is element C has a stress of minus 825 PSI. Okay. And since this stress is negative, that tells us that element C is in compression. Okay. All right, any final questions on this? Okay, all right, so that's all we got time for today. And so when we come back on Thursday, I have one more example to show you for 2D stuff, and then we'll jump into beam equations. So that'll become an interesting thing to do. All right, so thank you guys for coming today. Remember, your projects are due Thursday night, and so that is a non-negotiable deadline. So make sure you get it in on time, and I will see you guys all on Thursday.
I was wondering if these would be accepted with keywords.
Oh, don't worry about the keyword. Oh yeah, so on the report template, there's a keyword section. Don't worry about it. It's I keep forgetting to take that off the template, but you can just remove it. Those you can think of those keywords as kind of like the Google search words, but don't worry. You can just okay.
So for the formula thing, we had it back to like, a week and a half ago. So I had to redesign some uprights.
Okay.
Kind of a midterm project on those, just because I have to run FEA on them anyways.
You can do that for the final project.
For the final project?
Yeah.
Okay.
So for the midterm project, I want to do first. Final project is the choose.
Okay.
Yeah.
Okay.
I was just gonna ask about the conditions.
Yeah.
One of them I have a cooling because I'm using the handle.
Okay.
My scenario is there's a big problem, you gotta evacuate immediately, you don't care about anyone behind you, so you gotta launch the door.
Yeah.
So
Okay.
75 PSI in, 75 PSI out, and I made the handle 661 aluminum for
Okay.
all the scenarios. And then my last scenario would literally just be pulling but with steel.
So pulling and pushing. So what I really want to see from the two different motors is I want to see the stress. And so for pulling and pushing, you are going to see different stress. You have tensile stress, but you have to show that in the.
Yeah.
And so if you just show the equivalent stress, it's kind of about the same, but the magnitude of stress is probably going to be pretty similar. Pushing and pulling. There is a way to show compressive versus tensile stress. I think we did that in activity. And so just kind of make sure you do it.
Okay, either way, I was gonna make one where you're on the floor and then it's gonna be angled truss.
Oh, okay.
Like angled on the hand.
Yeah.
Like the pushing one's gonna be angled up.
Sure. You have a little asymmetry on it.
Yeah, so it's gonna be, alright, the pulling one's just flat, the back of the hand, but the other one's gonna be the little hook at the bottom.
Yeah.
I'm gonna use those two sides, like pushing outwards to try to push. things with it. And then for the last one, I just didn't know if I could really just do one of those two scenarios and just change it to steel.
Yeah, yeah. That's what I'm gonna do.
Okay.
You can come up with a third one if you want, but then you can alter this change.
I think I might do that.
Okay.
I think I might just do that.
Yeah.
Thank you.
Yeah.
I know what you mean.
Yeah, so I'm like, yeah, 75 pounds of force sounds about right.
Yeah.
For someone trying to get out.
Hey, I'm putting 120 on the handle, so.
Those all good.
I'm just saying, I weigh 160, so 75
When am I
half my weight, push it into a door.
Should I take another bubble and make one time?
Yeah, so don't get rid of change the handle,
I think
or change the, especially showing the railings. But yeah, if the stresses are on the back, I want to see what they show.
Okay, I think that's worse.
So, it's basically how it's laid it out. Like, on the page, couple of pages show the part abstract introduction. I think you did mention that we had the tables, on this also, like,
So I'd rather take the figures out, throughout the report, kind of like what we have now. The main data table that we need is actually material properties. So there's a section there where you have to describe kind of the Young modulus and the Poisson ratio, maybe the tension, maybe the density too. Yeah, so I'd like to have a data table, because most people are doing 2 and 2, so I'd like to see that one.
Oh, okay.
Yeah.
For the mention part, does anyone want to?
It will be as long as you need to specify, so remember the main things for your measure. Mesh size, and your mesh shape, and mesh form. If you want to make sure that all 3 of those are properly justified, so you should have a reason why. And for your case, you have, I think you certainly have to find that.
Yeah.
If you want to make sure you kind of justify why this is. So it can be really short, but I've seen good meshing sections where you like gave me very clear reasons. It could be just as simple as 1 or 2 sentences. This is why I pick the size, this is why I pick the word, this is why I pick the shape.
Like, something like this, like format be acceptable to like scenario one.
Yeah, no, that's
I
perfect.
was turning it into a paragraph, but I was wondering.
My story is.
Yeah, oh, that's perfect.
Thank you.
Very okay. You want to buy a product, one, so